And then we head over to the next speaker, Garrett Smith of Windfisher, a company situated in Grenoble in France. Thank you.
All right, good morning everybody. Garrett Smith, I'm the president and co-founder of Windfisher, and today we're going to talk about our Magnus effect kite. Is it going to go, Roland, or not? Can you just go through the slides and just one by one? I'll tell you when to change. So yeah, we've recently done a sizing and cost modeling for our system to help guide our engineering decisions and our estimated cost of energy when we get to maturity. Next slide. Hit the play button there with the mouse and we're good to go. So I just want to give you a quick overview of what our system is. It's a twin cylinder, inflated air beams that are reinforced with rigid structural tubes, carbon, and we have the rope to cylinder transmission, which drives, the ropes drive the rotation speed of the cylinders. And we're doing this figure 8. We're reversing spin direction between each side. So left to right, we reverse the spin direction. And this is really our first 3D animation, product animation, delivered a 100 kilowatt system in a 40 kilowatt container, in a 40-foot container. So the objectives really of our cost modeling are to get a better understanding of how our design parameters influence overall cost and where are we going as a company towards reducing the cost of energy. So we have to optimize some of the design variables and improve the cost efficiency. Next slide, Ro. This is our model architecture, so we've got a bunch of inputs. These inputs are things that we're going to choose and vary over the different combinations. We wanted to do a Monte Carlo analysis behind our model, and it turned out to be a little bit over optimistic as far as the amount of data that we thought we could get. But we're changing things like aspect ratio, the lifespan, the wind site characteristics, and that's giving us all the inputs to then do our physical model. The physical model then leads into basically the performance. What is our tether tension, the sizing of our O-wing, and that goes into the mass model, cost model, and we get all the way to the output. So I'm going to get into each detail. Next slide, please. So the steady state physical model requires, what is the rated power? That's one of our inputs, saying the client's going to specify the power. The aspect ratio, that really influences our aerodynamics. We have some Magnus effect aerodynamics that are in the literature, but it's not nearly as much as you would have for soft wing kites or for rigid wing kites. So we're extrapolating aspect ratio for efficiency L over D with some of our formulas. And the formulas in the lower left are the ones that we presented at the last AWEC in Milano. That physical model then gives us the overall performance and says what is the diameter of the kite, because the diameter of the kite plus the aspect ratio gives us the overall dimensions based upon the power input that we have. That gives us a tether force, the reel out power, and then with our power curve that we generate, and this is what our representative power curve looks like in our simulator, our 3D simulator. That then gives us our annual energy production. Next slide. So here's a better idea of the kite. There's two key things that drive the sizing. One is internal pressure. It's a pressure vessel, so the cylinder is inflated, and that's going to drive the actual, the sizing of the textile that's required to hold that pressure inside. And the internal pressure is based upon two things. One is the maximum operating speed, flight speed, or the other is the gust speed that we need to survive in case we have a storm go through. And the other one, it drives the aspect ratio. And the aspect ratio drives the rigid carbon that we have around, we got six carbon tubes around the cylinder. And so we're bending that. The critical driver is not how much bending moment we have. It's whether or not those tubes buckle. And the buckling is the critical parameter. And so we have to oversize those carbon elements to make sure it doesn't buckle. On the right, you see our prototype, existing prototype. So I can go to the next slide. As far as a tether and drum mass model, this is pretty much standard. Everybody knows this. We've done a model with electric generators and motors to drive the winch drums based upon much of the work that Rishi's done, that he'll be presenting, that has gone into our model here to give us the tether mass, the drum mass, and dimensions. Next slide. Then all of that comes into the cost aspect with the cost drivers, so performance and physical characteristics, put it into our cost model, and then we get all of our different costs. And then we're just doing a simple LCOE analysis. How much is it cost per year for the number of kilowatt hours that we're producing? Next slide. And this is probably one of the interesting ones for you, is to see how our system breaks down. So we've got about a quarter of it with textile for the initial textile at the delivery, and then one replacement. Our lifetimes are expected to be longer because we have a thicker textile with more coatings versus soft kites. Tether is expensive, that's for sure. And then we've got about a quarter over there for operation and maintenance. Next slide. This shows you how our cost of energy varies related to the aspect ratios. We initially started with aspect ratios of 6, saying that's the sweet spot for us with making it lighter than air. But it turns out that our cost model has informed us that, hey, an aspect ratio of 10 to 12, that's going to get the optimum for us because of the structural efficiency and the aerodynamic efficiency. Next slide. So going further, our model enables us to do technical trade-offs. Unfortunately, the model is not precise enough, in our opinion. It's a great learning experience for us, but it's not precise enough to let us, to give us complete confidence in our predictions. It's more of a qualitative model at this stage than a quantitative model. And so we need to go back to the engineering and say, hey, what are the detailed engineering models of each component, and how does that change for the cost? But we did find that we have a promising LCOE of under 60 euros per megawatt hour. O&M is the biggest uncertainty. Will our textile last 5 or 10 years? Will our rope last 3 to 5 years? We're not yet sure. And our biggest obstacle is fundraising. Once we get more fundraising, we're ready to roll. Thank you very much.
Thank you. Okay, we have questions.
One quick question. How are you planning to start and land the system? Is there anything?
There's two ways to do that, depending on whether we inflate it with helium or not to make it lighter than air. If it's lighter than air, it's an aerostat. It's just going to lift off of its container, so it's basically a vertical takeoff and landing. And we just have to control the dynamics of the flying during that phase to make sure it's done safely. If it's a heavier than air design, you'll actually see a video later in the OEM panel right now where we do hand launch to get it into the air. But the end discs can serve as landing gear. Those large discs on the side, they're perfect for landing gear. Okay. And that allows us to roll on the ground during our takeoff roll.
Okay, thank you.
Really fantastic presentation. So a quick question, did you consider tether diameter as a variable within your optimization? And if so, did you look at the kind of coupling between the optimal tether diameter and the optimal aspect ratio as your tether drag changes?
I'll answer the last part of that question first because it's the most interesting. We have huge lift coefficients. We're talking CLs of 8 to 10 based upon our aerodynamic performance. Tether drag does not impact us nearly the same as a profiled wing kite. You know, it's under 10% of the overall drag of the system. So we basically ignore tether drag in our most of our calculations because it doesn't have that much of an impact.
Awesome, thank you.
Thank you. Any other questions? Yeah, here, Lorenzo, can you just...
Sorry, and how about the tether mass instead, especially when scaling up? I think this becomes the main mass element.
We do model that in the system, and you know, the further away we are, the better we have in performance. But the further away we are, it's more cost, and so you know, there's the diminishing returns there. But we don't see it as a limiting factor in our design. So far, we haven't come to that any type of problem with the tether sizing or. I think the biggest key is that we're going to be we do 30-second cycles, so we're running this rope back and forth across the airborne drum. And so that's where the wear and tear on that is going to be one of our critical issues to study, to make sure that we're not having to replace that tether too often.
Okay, thank you
Thank you.
again.